called scaling laws. So in effect, models become reliably, predictably better as you increase the amount of compute used to train them. That's the model size and the amount of training data steps which are involved. Now, the clearest example of this is GPT-2 to GPT-3 to GPT-4 from OpenAI. These each, why is it going forward so many slides? Okay, so GPT-2 to GPT-3 to GPT-4. Each of these represented roughly a 100x increase in the amount of flops used to train them. And this progressed from something which had basic syntactical understanding to something which could reasonably answer some questions involved in high school, but had poor or mediocre performance, to a rather large increase in generalization and knowledge in GPT-4, to the level of roughly a smart high schooler. And the question I'm asking effectively today is, what if you thought that you could do a couple more perceptual leaps like the one between GPT-3 and GPT-4? On the face of it, this seems like a ridiculous extrapolation. This is an extrapolation as far as progress on this slide indicates. But if we go to the next slide, it's actually not that much further than the lines established over the last 4 years. So in the original 2020 paper on, scaling laws, they found 10 orders of magnitude over which these lines didn't bend. GPT-3 established another 2, and GPT-4 established another 2 after that. So rather than expecting you to extrapolate over a basically effective doubling of the horizon here, I'm asking you to consider what would it mean if we could hold on just a little bit longer on that straight line, towards something capable of performing something like 50% of services economy GDP. Now, to illustrate the jump between something like GPT-3 and GPT-4, I use these reference classes, one, because it allows me to estimate the flops that we used in, say, GPT-4, whereas I'm not allowed to do that with Gemini, but also because they provide nice reference classes. It goes from poor or middling performance in many high school and analytical exams to, frankly, incredibly good performance at high school exams. This is still reflective of a spiky and, frankly, not that generalizable intelligence, but it's a pretty stark jump in both reasoning and knowledge. Now, unfortunately, there is this relationship that DeepMind established in 2022 called the chinchilla scaling laws, which indicated that compute was contingent on data. You had to scale both, in effect, together. And this has led many to ask whether or not there might be a data wall that brings us off this scaling trend. Whether or not this is true is up for debate at the moment. I'll leave you here with two quotes from Anthropic and from OpenAI about whether or not this might be true. In both cases, neither one believes it benefited imminently, but they think that it will change the nature of pre-training. But so far, all I have to ask you to consider is what pre-training scaling might look like. That is, scaling the model size and scaling the amount of data input into the model. Ilya Sutskever, an ex-co-founder of OpenAI, asked a provoking question when he was starting his new company about 2 months ago, which was, everyone always says scaling laws, but everyone forgets to ask, what are we scaling? The parable of deep learning research over the last 4 years has been Richard Sutton's bitter lesson. It's bitter because as AI researchers, we would dearly love to be clever. We want to inject our priors into how the models learn so that they can learn better. But ultimately, these priors only end up harming the generalization ability of the model. Richard points to 2 things which scale: search and learning. Pre-training is an example of learning. It's an example of how, as you let the model learn, it's able to accomplish dramatic things, but it's still speaking mostly off the cuff. In effect, it's never allowed time to reason or think. It has to immediately begin blurting out tokens in a response. Search is the act of giving the model some time to reason or think, which is not something language models have done up until very recently. Initially, search and learning were combined by DeepMind in the AlphaGo series of models. This is something I'm sure familiar to you from many years back, where we combined search and learning to achieve superhuman performance on Go. And there's this beautiful GIF on the right, where you have a model that learned not from human expert demonstrations, but actually from purely playing against itself. And over the course of about 40 days, it swiftly exceeded human-level performance in what was previously regarded as an uncomputable domain. But does this apply to language models? So this isn't language models, but this is the first instance of a scaling law for what's called test time compute, or scaling law for allowing a model to reason. This is from an Anthropic researcher called Andy Jones, who studied, again, board games. And what you see on the x-axis is the amount of training time computed, so the learning from Richard Sutton's lesson, in terms of how smart you make the base model. The y-axis is how much time you give it to think or to reason about what it is allowed, what its move is going to be. And it finds a consistent relationship, a power law relationship again, between the ELO of the model and the combination of training time and test time, scaling laws. OpenAI last week released a language model which was able to use search in the loop. And in particular, I want to call out the GPQA diamond results. So GPQA is a set of PhD-level STEM questions which are regarded as ungoogleable. They're extremely well designed, they're extremely tough. I encourage you to try any of them if those are your field. I've tried them, I find them extremely difficult. And the GPT-4o1 achieved PhD or exceeded PhD level performance at these questions that require an intense amount of reasoning that are honestly, frankly, extremely difficult. And most importantly, they found again a consistent relationship between the amount of time afforded to the model to think and the performance of the model on extremely difficult tasks, like the AI math exam. Now these are still, all the examples I've shown you so far are discrete, concrete problems, which don't require huge amounts of context. We still haven't solved all of those things in language models, but it is showing that they are able to progress up this chain of reasoning capability within certain domains. Again, within a certain domain, DeepMind recently got an IMO silver medal. And to give you an idea of how fast an acceleration in research progress this indicates, in about 2022, the average prediction for when an IMO gold medal would be achieved was 2035. Now it's next year because of this result, which again combines search and learning with language models into the loop. But do we have actually any evidence that these things are able to reason at all? I mean, there is performance on all of these tests that we use to measure human reasoning, but you could argue that they're just interpolating between questions that they've seen before. Even if this is still an unanswered question, are they truly able to extrapolate? But then a question worth asking as well is how many of the tasks that we do as part of our jobs require huge amounts of extrapolation? I certainly find that I'm at least 3 or 4 times faster in new programming languages than I was before language models. I'm 20–50% faster in my existing programming languages. Coding is the kind of thing that falls first to language models because the data sets of how we interact with the world exist online for them. Some piece of evidence I like about the beginning or the emergent evidence there might be some level of world model or some level of generalization in these models comes from a field called mechanistic interpretability, which is the science of how to pull apart these language models. Where simple language models learn board game world models inside them, all you do is ask them to predict the next character in transcripts of games. They find that the simplest way for them to learn to do that is actually construct a world model that you can pull out and causally intervene on. Concepts such as days of the week exist in circular structures within the latent space of models. And there are also just cute examples of generalization, like Gemini 1.5 getting human linguist level performance on an unseen language, which it didn't have any example of in its training data. So the question I asked you to then consider is, one, what would the world look like if we were able to scale a little bit further? And how many jumps of this magnitude would we need? Terry Tao puts it well, which is that the jump between GPT-4 and the model GPT-o1, which it allowed to reason, or the introduction of test time compute, was the difference between a mediocre graduate student and an incompetent graduate student, but still a graduate student. And that 1 or 2 more iterations of this form, like the jump between GPT-3 and GPT-4, might bring about a reasonably competent graduate student, which is an utterly terrifying concept, or amazing, depending on your perspective. This is a graduate student in everyone's pocket, or the ability to deploy thousands of graduate students on any task or any field of human endeavor. And what test time compute scaling brings is effectively an orthogonal axis along which to scale. You have here the pre-training scaling going on like this. The test time compute brings an entirely new jump in model capability, and in effect affords you the ability to not have to invest the training compute to get a certain level of capability. And so the question then becomes is Terry Tao right? Do a couple more jumps along these axes give us an average graduate student that we can deploy to any task that we want? The field as a whole is on one of the most ambitious capital build-outs of all time to find out. So this graph is pulled, or this table is pulled from an essay called Situational Awareness by a friend of mine called Leopold Aschenberg. It's worth reading for more on this topic. But in effect, it plays out those orders of magnitude. Remember that those jumps are each associated by a 100x increase in the amount of compute required. So to answer this question of whether or not there is AGI at the end of this scaling relationship, or whether those lines bend, is going to be an expensive one. You can look at it in terms of dollars, or you can look at it in terms of the percentage of US electricity production. To explore those extra orders of magnitude will take meaningful fractions of US energy production, which is utterly absurd on the face of it, but over the next couple of years, you're in effect going to see each of the major hyperscalers running ahead of each other to try and find out the answer to this question, because the lines haven't bent yet, and what lies at the end of it is incredibly exciting if they don't. Thank you. Hope this was thought-provoking, and I hope it gives you some points from which you can go and read further on the topic. Happy also to discuss any of this with anyone else after the conference.